So I was asked if I graded the quizzes, and like I said, I looked at a few of them, and I didn't grade them all. I'm battling something. Maybe one of you all brought it in, and I'm infected with it now. But I'm trying to get over an illness myself. I've got to teach first and seventh period today, so I'm kind of stuck here the whole time. Yeah, I'll try not to cough in your direction. But one of the things that became clear by going over the quizzes is that we need to spend more time on building covalent molecules. Okay, there's really a fundamental misunderstanding or lack of understanding. And hopefully, when you took the quiz yesterday, if nothing else, it made it real to you that you need, for some of you, not all of you, but that's the case of teaching a class, not for everybody. But some of you really need to have a better process, a better understanding, or confidence that you have a strategy for drawing the Lewis structures for covalent molecules. So what I thought we'd do today is I've created 3 different slides for PowerPoint that go through different techniques, 2 different techniques for drawing the Lewis structures for covalent molecules. One is the structure or the technique that I've been teaching you, the technique that I use. The second one more closely follows the book's method. Now the book's method is not my method. I had to sit down yesterday and go through and read it just as you probably did, trying to make sense of it. And I've added a few steps or tweaked it a little bit in a way that makes it easier for me and I think makes it easier for you. But what I'd like to do today is just go through the quiz, go through some of the molecules that we were supposed to build using the technique, the process for building those molecules, so that when you take the exam, you're confident that at least you have a process for figuring out a molecule you've never seen before. You've got a process of how to solve it and draw it correctly. All right? That's my intent. Now, originally we were going to do the module exam on Monday, but that would be bloodletting right now if we did that, okay? We're not going to do that on Monday. There's no way. So we're going to have to push it off till probably about Wednesday, just to get some of this material down, not only for you to learn it again today, but then to become even more confident that you know what you're doing. Hopefully, quizzes and tests, you feel you know what you're doing, and then in the middle of the exam, you find a few of them that you got to apply yourself a little bit more intently to, but you're confident that you can cover the material. As a class, I don't think you're ready for the exam. So we're going to extend our time in this module a little bit longer. And part of it, too, is not this group. I get asked all the time, how does our class compare to last year's class, to the year before that, to the last 10 years you've been teaching it in homeschool, co-ops and things like that? We got hit with several days where a group of you were absent, okay? And yesterday's quiz really was painful. And also, I just want to remind you, the lectures are online. They've been going online on the same day they've been given. So I know that you probably have other work to make up as well, but the material is there for you. And so giving you tonight, the weekend, kind of catch up on actually watching the lectures, I think that'd be significant as well. So the 3 different slides I have, now unfortunately I developed them in a PowerPoint that's a little bit more, it's newer than the one that's on this system here, so all my animations don't work. So I'm just going to go with the flat screen. I was going to have each one of these bullets fly in and all that kind of stuff. So it's going to be pretty flat screen. Now, I do have copies of these slides for you, and I'll give them to you when you leave. I'm not going to give them to you now because I want you to be writing in your notes, seeing the information and writing stuff down. What? Was that asking too much? Okay. I speak cough. I want you to go ahead and feel like, okay, I want to remember that. I want to write stuff in my notes because hearing it, processing it, writing it helps you remember it. But just know when you leave, you're going to get a copy of these 3 slides that I give you. All right. So when asked to write a Lewis structure, for example, I asked you yesterday to draw the Lewis structure of sodium chloride. Had you answered this question, many of you would have done it differently. What elements combine to form the molecule, sodium chloride, is sodium and chlorine, right? Second, is the molecule ionic or covalent? How do I know? Well, if there's a metal involved, the molecule's ionic. Well, sodium chloride, sodium is a metal, right? So it's ionic. So there are no covalent bonds. There are no lines drawn in a sodium chloride molecule. It's ionic. So if you had anything with a sodium and a chlorine with any kind of bonding between them, it was wrong. Because sodium chloride is ionic. What happens in a sodium chloride between a sodium and a chlorine? A sodium is a column 1 element, so it would have a single electron. A chlorine is column 7. Okay? And remember what happens in ionics. The sodium gives up its electron, it transfers over to the chlorine, then they become oppositely charged and are attracted to one another, and the sodium then moves over to, or vice versa, but they move together and they are bonded together. So that is the Lewis structure for a sodium chloride ion, or excuse me, a sodium chloride molecule. There are no bonds in an ionic molecule. So anything, again, that had a bond between them was wrong, because it was ionic, because a metal was involved, the metal being sodium. Now, if all the elements are nonmetals, then it's covalent. Okay? If everything is a nonmetal, then they bond by using little bond lines, sharing electrons. And I made this note down here, there are no molecules which involve only metals. Okay? There are only molecules that involve metals and nonmetals, which are ionic, or nonmetals only, which are covalent. There are no metal-metal molecules. So then, conceptually, how was it formed? Well, if it's ionic, that's what I just described with sodium chloride. If it's ionic, electrons are given, not shared, given and received, complete the octets, opposite charges attract, and they're stuck together. In covalent molecules, meaning all nonmetals, then electrons are shared. Shared electrons are called bonds. Single, double, triple bonds. Covalent molecules only, meaning non-metals only in the molecule. All right? So those are the questions you have to ask before you even decide, am I going to draw this with bonds or not? Ask the question, is it ionic or is it covalent? Now, here's a process using the method that I use for drawing a molecule. Let's go ahead and pick one from the quiz, or I'll pick one from the quiz. It's kind of an easy one to start off with. And we're going to, let's say the question was, draw the Lewis structure for, we had NF3. So NF3. We've looked at that and said, you know what? Those are both nonmetals. Therefore, I know this is a covalent molecule. I've got to build the structure for this covalent molecule. Okay? It's very hot in here right now. Okay? I know I'm ill, so I probably feel warmer than you do, but it is warm in here. If you have to stand up, please do it. Okay? Please don't fall asleep. So, write the chemical symbols for the elements involved. Why is that funny? I'm trying to figure out, why is it funny when I'm asking you not to fall asleep? Okay. Guys are an interesting group. NF3, write the symbols that are involved. What's involved in NF3? Well, obviously it's nitrogen and fluoride, right? Or fluorine. Nitrogen and fluorine. We're going to have 3 of them. Remember, that's what the 3 represents over here. This isn't like the transition metals where I'm giving you a Roman numeral, and the Roman numeral represents the charge. That 3 tells us that 3 ions or 3 atoms of fluoride or fluorine are going to be involved with 1 atom of nitrogen. I'm just going to draw the 1 fluoride right now, 1 fluorine right now, while we go through this. So complete the Lewis structure for each element. I have to do a Lewis structure for nitrogen and a Lewis structure for fluorine. Nitrogen, I'm going to go to the periodic table and see that that's a column 5A element. Column 5A means that it has how many valence electrons? 5. It has 5 valence electrons. Now, one of the hints that I gave you when you build these structures, remember we talked about completing the Lewis structure, we start at 3 o'clock and go around. One of the things that you'll learn over time is that when you have a column 5 element, they're often the hub element. They're often in the center. So column 4s and column 5s tend to be what's in the center. And column 4s, since they just have a dot on every coordinate point, that works fine. But for column 5, just visually for us, since we always think up and down and right and left, the way we're oriented, It's going to help you in the future when you use column 5 elements is to always write the paired electrons on the top. Put the 2 on the top. If we did it the way the book said, it'd be 1, 2, 3, 4, and then you'd have a paired on the right. But it'll help you out because column 5 elements are going to end up with 3 things bonded to them. For the most part. 3 things bonded to them. And again, how we're oriented, what makes sense to us, having the top doubled the pair, we'll see later on that other things form around it. So nitrogen has 5. There's 2, 3, 4, and 5. Build up the fluorine. It's a column 7 element, correct? Yep, column 7A. 7A means 7 valence electrons. And I'm going to orient the, just for looking at it this way, I'm going to orient the unbonded electron towards my other atom. It's going to help me visualize this a little bit better. So 7 around that. 1, 2, 3, 4, 5, 6, 7. Bad strategy in a hot room when you're tired is to lay your head down, right? Like, not a good strategy. Okay, so we've got 7 around the fluorine, or fluoride, fluorine, let me keep it at that, fluorine, 5 around the nitrogen. So I can visualize what this is going to look like. I'm going to have 3 of those fluorines. I've only shown 1 on the board right now, but I'm going to have 3 of them. But I can see 7 around the one, 5 around the other. Place the atom with the most unpaired electrons in the middle, between the 5 and the 7, which has the highest number of unpaired. You see that these 2 are paired. There's a pair, here's a pair, here's a pair, here's 1 lone. I have 1 unbonded electron in the fluorine. Nitrogen, I have a pair and 3 unbonded. The 3 unbonded, between these 2 different elements, nitrogen has the highest number of unbonded electrons. Therefore, it is going to be in the center of my structure between these 2 elements. Okay? Then, it also says here if there's more than 1 element in the formula, in other words, if this was an N2, if there were 2 nitrogens, for example, then I would put those in the middle and I would bond them to each other. Whatever has the highest number are going to go either, if it's 1 of them, it's going to be the very center. If it's 2 of them, they're going to connect to one another in the center. Yes, sir? Yeah, if for example, it was some molecule that had an N2, a subscript 2, that would mean that there are 2 nitrogens in that molecule, and I would put them both in the center. Normally what it's going to be is carbon. Like if you had a C2Cl4 or something like that, you say, well, carbon would be in the middle, but I've got 2 carbons. How do I deal with that? They go with each other in the center, and they're going to be bonded to one another in some way. So arrange the other elements then around the center element or elements and look for symmetry. We're going to have 3 fluorines and 1 nitrogen. How are those 3 going to orient themselves around the center? Well, I said 2, look for symmetry. And already this is a column 5 element, and I'm anticipating bonding to those 3 points, right? So fluorine, I've got a bonding point here with a single electron and 3 single electrons here. I'm going to orient my fluorine elements around the nitrogen, and I'm going to place the unpaired electron towards the center. So I place the appropriate number of Lewis dots around each element with an unpaired electron from each exterior element facing an unpaired electron from the center element. See, here's my unpaired electron. I put it towards the center, unpaired towards the center, unpaired towards the center. Then I replace my facing electrons with bond symbols. There's got to be some form of a bond for these elements to even be held together, right? They've got to be some kind of a bond. Otherwise, it wouldn't be an NF3 molecule. There has to be at least a single bond. There may be a double and maybe a triple, but there has to be at least a single. So what I'll do is go through and replace facing unpaired electrons. I'll pair them with each other and make a bond. So this unpaired here, unpaired here, unpaired here, forms that structure. So I've replaced the unpaired facing electrons with a bond. Now I'm going to go through and check to see if the octet rule has been satisfied. Is the octet rule satisfied? Don't forget to check the center element as well. Let's go around the outside. Fluorine, what does it see? 2, 4, 6, 7, 8. 2, 4, 6, 7, 8. 2, 4, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. The octet rule is satisfied for every element on the board, so we're done. Okay? Now the process would go on and say, check that it's satisfied. If it is, if it's not satisfied, we've got to use more bonds, right? The only way we can satisfy the octet is through bonding other electrons, forming other bonds, sharing other electrons. So after we check for satisfaction of the octet rule, then we're going to pair unpaired electrons between the elements to fill in the octets, make more bonds. And if one element's octet is full, but its neighbor is lacking, we'll get into a few of these, then we're going to pull a pair from the one that's full. See, if I'm one element and I already have my octet full, and I'm bonded to a neighbor, and the neighbor is short 2, okay? There's no place else for us to go to get electrons other than to give up mine. If I have 8, I take a pair and I form a bond, have I lost any? Think about that for a minute. If an element has its octet full through paired electrons, and it takes one of its own pair, it gives up 2 electrons to form a bond with its neighbor, does it see more, less, or the same number of electrons? Sees the same number, right? Because the 2 that it owned exclusively, it now shares both of them. Okay? So it still has its octet full, but by sharing a pair, what does the neighbor pick up? The neighbor picks up 2, right? So that's how you're going to count around and say, hey, wait a minute, the octet of the neighbor is probably down by 2. Let's say one octet has 8 and one octet has 6. How are we going to make them both have 8? The one that has 8 is going to take a pair of electrons and make it a bond. It'll still see 8, but now the neighbor will also see 8. Okay? Let's go ahead and just leave this method on the board, and let's do a few different molecules, and then we'll flip over to the apologia method and do a few molecules with them as well. So this is the NF3 molecule. What was one of the other ones we did? Let's go ahead and do the SiS2, silicon sulfide, disulfide, right? Because it's covalent, we got to use the dis, tris, and all that in the naming. So it's SiS2. So if I was asked to find the formula or draw the Lewis structure for SiS2, there is no element I, that's not iron, lowercase iron, right? It's Si and S. So silicon and sulfur. My 2 are silicon and sulfur. And by now you know silicon is how many valence? Without even looking, right? It's just like carbon, which is 4. One of our primary hub elements. We're going to have 4 dots around silicon. And sulfur, column 6, just like oxygen. So I'm going to go ahead and put 2 and 2 and put 2 unbondeds like this. Okay. Of those 2, which one has the highest number of unbonded electrons? Unpaired, unbonded. Sulfur has 2, silicon has 4. So silicon's going to be my hub. Also, with that logic, think about symmetry. SiS2, I've got 1 Si and 2 S's. Somehow the symmetry is going to be formed with the single element in the middle and the other 2 around it, right? I'm not going to have 2 silicons in the middle and sulfur, or 2 sulfurs in the middle and a silicon hooked to it. That doesn't match my symmetry requirement. So I've got to put 2 sulfurs up there. I've already got 1 unbonded electron towards my center element, and for symmetry's sake, I'm going to put the other one on the other side, and I'm going to orient it with an unbonded electron towards the center element as well. So place the atom with the most unpaired in the middle, arrange the other elements around the center element, trying for symmetry, place the appropriate number of Lewis structures around each element with an unpaired electron facing the interior element, replace unpaired facing electrons with a bond, okay? Now I'm going to go through and form my first bonds. I know that in order for these things to even be in the same molecule, there has to be at least a single bond between them. And I'll form that single bond by replacing these two facing unpaired electrons and forming a bond, and these two facing unpaired electrons and form a bond. That's my start. Check for the octet rule. See if it's satisfied. 1, 2, 3, 4, 5, 6, 7. No. 1, 2, 3, 4, 5, 6, 7. No. 1, 2, 3, 4, 5, 6. No. It's not satisfied. Okay? We have to pair unpaired electrons between the elements to fill in the octets. So I'm going to look for unpaired electrons and see if it'll get me closer to or accomplish filling the octet rule. Look over here for an unbonded electron. Here's an unbonded electron. Let me just go ahead and rewrite it over here to the center. Let me take this unbonded electron as well and put it to the center and form a bond. When I do that, each of those elements is going to pick up one electron. Okay? 1, 2, 3, 4, 5, 6, 7, 8. This sulfur now is satisfied. Its octet is full. Let me do the same things for symmetry. Let's do it to the same thing on the other side. I'll bring an unbonded there, and and pair them. 1, 2, 3, 4, 5, 6, 7, 8. And now looking 1, 2, 3, 4, 5, 6, 7, 8. Every element's octet is complete. We're done. Okay? Now technically, yes, we're going to learn that these would shift off to be 120 degrees apart and all of that. But if you got that, I would be thrilled. Okay? For where we are right now for this module. Next module and following modules, we're going to perfect this a little bit more. But for right now, I should see 2 bonds and 2 sets of paired electrons. I'm going to keep track of what we did using this method, and we'll do it the other method in a minute. So we did NF3, SiS2. Let's do one that has a kind of a... Let's do that CS molecule. That's kind of interesting. CS. The two elements involved are symbols C and S in a CS molecule, right? So carbon, again, not much thought there. Carbon has 4. Sulfur, 6. 1, 2, 3, 4, 5. I'm going to put it unbonded towards the center. There is no center now, though, right? There's only 2. There is no center. But I'm going to face 2 unpaired electrons towards each other. And in order to have some semblance of any kind of a molecule, I'm going to replace those 2 with a bond. Now I'm going to check the octet rule. 1, 2, 3, 4, 5. Nope. 1, 2, 3, 4, 5, 6, 7. Nope. Okay. So, since they're both short, they're both going to contribute. I'm going to take one of my unpaired, the other unpaired from both sides, and replace them with a double bond. 1, 2, 3, 4, 5, 6, 7, 8. Sulfur is satisfied. It's got its octet. Carbon. 1, 2, 3, 4, 5, 6. It's not satisfied, right? Carbon doesn't have enough electrons. So, replace facing, check for octet, pair unpaired. If one atom's octet is full, and its neighbor is lacking, that's this situation, isn't it? One is full and its neighbor is lacking. Pull a pair from the full to form a bond between them. So, if I were to take 2 electrons from sulfur and form a bond, sulfur hasn't lost any electrons, but carbon has gained electrons. You see that? Okay. So sulfur still has 1, 2, 3, 4, 5, 6, 7, 8. Carbon now has 1, 2, 3, 4, 5, 6, 7, 8. Octets are full. Last step. Pair unpaired electrons around the elements. The carbon has 2. Because of the process, it's still showing 2 unpaired electrons, but its octet is full, I'm going to bring this over and pair them. There's the Lewis structure for the CS molecule. Let's do one more using this method. Let's use the CCl2S molecule. CCl2S. Carbon has 4, chlorine has 7, sulfur 5 or 6, right? So which one has the highest number of unpaired electrons? Carbon does, right? Carbon does. So we'll draw the carbon. I'm going to do a new diagram since we have to make sure we do 2 of these, right? CCl2S. So carbon, though, is going to be my centerpiece. I now need to place 2 chlorines and a sulfur. I like to, again, I always try to use the symmetry, so I'm going to go put the 2 chlorines across from each other. I'm going to do the electron diagrams with a unpaired electron facing the center. So there's my 2 chlorines, my center carbon, and now we need to place a sulfur. I'm going to draw the sulfur here and put my 1 unbonded electron towards the center, place my other 5 like that. Okay. Arrange the other elements around the center elements, trying for symmetry. Place the appropriate number of Lewis dots around them. I've done that with unpaired facing the center. I've done that. Replace the unpaired facing electrons with a bond. Bond those 2. Bond those 2. And share those 2. Okay, so there's my initial attempt at the molecule. Not saying it's right, but there has to be at least a single bond between those atoms to hold it together to form some semblance of a molecule. Now we're going to go back and see if that's the final form or not. And we do that by checking the octet rule. Chlorine, 1, 2, 3, 4, 5, 6, 7, satisfied. 1, 2, 3, 4, 5, 6, excuse me, 1, 2, 3, 4, 5, 6, 7, 8, it's satisfied. 1, 2, 3, 4, 5, 6, 7, 8, it's satisfied. 1, 2, 3, 4, 5, 6, 7, it's not. 1, 2, 3, 4, 5, 6, 7, it's not. I'm going to look for unpaired, unbonded electrons and bring them in proximity to one another on the diagram and then replace them with a bond. I have an unpaired electron here. I'll bring it towards the center. Unpaired electron here. Bring it toward the center. Share them. 1, 2, 3, 4, 5, 6, 7, 8. Carbon is satisfied. Sulfur. 1, 2, 3, 4, 5, 6, 7, 8. It's satisfied. There is a legitimate Lewis structure for CCl2S. All right, so that's the method that I use. This is the way that makes sense to me. This is the way I've been doing it for, 30 plus years. So when I'm doing it in my head, when I'm helping you, this is the way I default to. Yes, sir. So what I'm going to do now is replace this and put on the board the Apologia method the way they use it. And I'm not going to say that I perfectly represent their method, because I view their method through the way that I've been trained to do it. So it might even be a tweak. If you've studied their method, you might see it a certain way, slightly differently than the way I've interpreted it. But it is a way. It does work. It's just not the way that seems natural to me. We're going to follow their process and try to build these same 4 molecules using their process, slightly differently. Okay. Let's form the molecule NF3. Their process starts with count up the total number of valence electrons in the molecule. So the way I would do this on my paper, I've got nitrogen. I've got one of them. How many valence electrons does nitrogen have? Okay, if you're looking over there, either you know it or you're looking over there, or maybe a periodic table in your book, and you're saying, hey, it's a column 5A element, therefore nitrogen has 5, right? So the nitrogens contribute 5 valence electrons. The fluorine, I have 3 of them. Each one donates how many valence? 7 each for a total of 21. So there are 26 valence electrons that we're going to have to place for an NF3 molecule. So we count up the total number of valence electrons in the molecule. Okay. They start with, again, the same way that we would on the last one. Place the atom with the most unpaired electrons in the middle. That, again, we said was nitrogen, right? And arrange the other elements around the center element looking for symmetry. Okay? So it would look very much like what we did for the first time, only this time there's no dots around it. We're just going to draw the symbols. Arrange the other elements around the center element with symmetry. Basically connect the elements to the center element. So we're going to go through, like I said before, there has to be some bond to hold it together to form a molecule in the first place. We're not sure that's the final form, but it has to be at least that. Maybe a double bond, maybe a triple bond, but it has to be at least a single bond. Okay? So connect the external elements to the center element with a single bond. Reduce the valence electron count by 2 for every bond that you've just drawn. How many bonds did we draw? 3 represents how many electrons? 3 bonds is 6 electrons, right? So we're going to subtract 6 from our count here, which leaves us 20 electrons that we need to place. Let's go through and place 20 electrons, filling up the valence shells as we go. Starting from the outside, and then any leftovers go to the middle. That's the technique I would use. So we want to have 8 around fluorine. It's got 2. 1, 2, 3, 4, 5, 6. I've placed 6 electrons. Minus 6 leaves me with 14. Place another 6. Minus 6 leaves me 8. Place another 6. Leaves me 2. Check the octets. 8, 8, 8, 8. We're done. Like I said here, make sure you check the center element for the octet. And just like before, if one is lacking and the other one's full, pull from the full to form a bond with the lacking. All right? So we've done both of those. Let's try the SiS2 molecule. Yes?
It says if one is lacking, pull from the other. And that's where you take a pair and
Form a bond.
share, but you don't give them any.
Right. You share. One element is going to share 2 rather than just sharing 1. The other one's going to receive 2 and not give up any. Correct. SiS2. Okay. Si. One atom at 4 valence each, right? Sulfur, we've got 2 of them at 6 each for a total of 12. SiS2, that's the formula, yeah. So SiS2, 2 sulfurs, 1 silicon, total of 16 valence electrons. I'm going to go place the atom with the most unpaired electrons in the middle. Si has 4. If you have a column 4 element, it's generally going to be the center element. Yes? Formula is SiS2. I just haven't drawn the other S up there yet. SiS subscript 2. That means they have 2 sulfurs and 1 silicon. So when I place them, the atom with the most unpaired in the middle, and arrange the others for symmetry, my other silicon's going to go over there. Or excuse me, my other sulfur is going to go over there. See the straight line symmetry. So I have Si and the S's. Connect with a single bond to start with. 2 single bonds use up how many electrons? 4. So I'm going to reduce my total of available by 4, meaning I have 12 left. Okay? And again, I haven't used their method on every one, so I'm with you on this now. I'm making sure their system works for me. This is not the way I would do it, but it is a valid way. Every time I've tried it with other molecules, it's worked. So arrange them around the center, try for symmetry, connect with a single bond, reduce the valent count, we did that, evenly distribute the remaining electrons to the external elements, and then we'll fill in from there. So we've got 12, right? Let's go ahead and start filling on the externals. Well, we've got 2 with 6 apiece. That'll take them all, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 for a total of 12. And we're done. We have no more electrons to play with. Does that satisfy the octet rule? Well, it does for the externals, right, for sulfur, but not for silicon. Go ahead. Yep. If one atom's octet is full and its neighbor is lacking, pull a pair. Just like we referred to before. So as we look at this, sulfur is this one's done and this one's done. They're both satisfied, right? But silicon's in the middle saying, hey, wait a minute. This isn't fair. You know? This isn't fair. I'm not getting my fair share on this deal. How do we make it fair? Well, silicon is lacking. It only has 4. It needs 4 more. How do we get that 4? Using the rule that says if my octet is full and my neighbor is lacking, we pull a pair. That means, okay, I pull a pair, I take 2 from here and make a bond. That sulfur still has an octet that's full, but I've just increased silicon by 2. Now this has 8, but this only has 6, and for symmetry's sake, I need the other pair over there. Now, both sulfurs have 8, silicon has 8, octets are complete. That is your Lewis structure for SiS2. Okay? So you see the alternate method, how this works? And probably the most difficult thing to see is if one is full and one is lacking, you pull from the full to bond with the lacking. Pulling from the full to form a bond does not lose any from the full, but it gives 2 to the lacking. All right, third molecule, CS. 1 carbon, 1 sulfur. Carbon contributes 4. Sulfur contributes 6. We have a total of 10 electrons to play with. We form a single bond, consumes 2, leaves us with 8. Let's take the 8, split it in half, and share it. So the 8, we're going to give 4 apiece, let's say. Okay, now I've used up my whole set of 8, right? 1, 2, 3, 4, 5, 6, 7, 8. They're all used up, so I don't have those numbers to play with anymore. Now I have to build it all just from shifting dots around here. Is either one satisfied? No. Let's start by bonding unpaired electrons. I'm going to move 1 unpaired and 1 unpaired, bring them over here and bond them. Are they satisfied? No. Start by another unpaired set. Unpaired and unpaired, bring them to the middle and bond them. Are they satisfied? Yes, they are. Now, for symmetry's sake, we could perfect that by bringing these paired electrons over. That is your CS molecule, a triple bond. The triple bond there is the strongest bond we're going to deal with, right? We've got single, double, and triple. The more bonds, the stronger it is. Another way to say it, the more energy it takes to break it. Lastly, the CCl2S. This should be interesting. Let's try this one. CCl2S. So I've got carbon. Carbon is 1 at 4. It gives me 4 valence. Chlorine, 2 at 7 gives me 14. Sulfur, 1 at 6 to give me 6 and 24, right? I'm replacing 24 valence electrons. The highest number of unpaired carbon, it's column 4. Column 4 or column 5 is generally going to be your hub. For symmetry, I'm going to put the chlorines on both sides and a sulfur. I'm going to start by bonding all of them with single bonds. How many single bonds? 3. How many electrons consumed? 6. So I subtract 6 and leaves me 18 to play with, right? 18 going around how many? Between 3. I can place 6 each, right? If I place 6 each. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. How's that work? That's all of them, right? That's all of them. Okay. So I'm going to get rid of my electrons here just to clear the board a little bit. There's my 18. How does that look in terms of the octet? Chlorine, 1, 2, 3, 4, 5, 6, 7, 8. Is it set? Chlorine and chlorine are both set. Sulfur, according to the way we've drawn it, it's set. Carbon, carbon's getting ripped off, right? Carbon's getting ripped off. What are we going to do? Take a pair and share from where? See, this is one place where my method makes it clear, and this method kind of makes it fuzzy. But think in terms of symmetry. If I have a chlorine and a chlorine to a carbon, if I double bond one of the chlorines, I've thrown the symmetry off, right? Then I have a single bonded chlorine and a double bonded chlorine. That's not symmetrical. So I would defer to the lone man out. In this case, sulfur, fork up a pair, okay? So since it has 8 and carbon has 6, we pull a pair from the full to share with the lacking by forming a bond. We're going to pull 2, form a double. Sulfur hasn't lost any, carbon's gained 2. Now every element has its octet satisfied. And that is your Lewis structure for CCl2S. Okay? I won't take it personally, but how many people like my method better? Okay, how many people prefer this method? You see that you could do, okay, that's fair. Do you see that you could do both of them? To check yourself too? And what I want you to do is whichever one works best for you, so that when you're doing this, you're confident you know what you're doing. For me, the only of these 4 molecules, the only one that makes more sense to me to use my way is this last one. Because this one, if I'd drawn the appropriate number of valence electrons around sulfur, would have shown me that that's where my double bond is going to be. I would have seen that much earlier. Okay, but both methods work. The only thing that makes me know to take it from sulfur is symmetry. Okay. One other question we can maybe finish with today. So I want to do let me go ahead and kill the projector because you don't need the light shining back on it. One other question from the quiz. Let's work through what is the name of the ionic compound PbO2. PbO2. Yes. It is lead oxide, but it's not enough information, is it? Okay. Is this ionic or covalent? It is indeed ionic. So the charge from the lead and the charge from the oxygens have to balance each other, don't they? So I've got lead over here, which has a yet to be determined charge. And we have oxygen over here. Each oxygen wants to take on what ionic form? What charge does each one want to have? Wants to go to 2 negative, right? It's column 6 element, so it wants to have a 2 negative. But I have 2 of them, right? So the oxygens are going to contribute what to the molecule? A -4 charge. 2 oxygens, each going 2 negative, is 4 negative. My metal has to give me enough electrons to fill that 4 negative and have a counterbalanced charge. So it has to have 4 positive. 4 positive at 1 atom means that it's going to be lead 4 oxide. Lead 4 oxide. Okay? Because the lead, whatever the metal is, has to balance with the opposite sign, same number, opposite sign of whatever the non-metal, or excuse me, whatever the non-metal ionic is going to do. 2 O2s, we know that oxygen always wants to be 2 negative. It always wants to be 2 negative, and I have 2 of them, which means I'm going to have 4 negative charge. The metal has to balance the 4 negative. If it had been Pb4O2, then it would have been lead 1, because I'd have 4 at 1 would be 4. But since I only have 1, it has to make up the whole charge to counterbalance the 4 negative. So it has to have a 4 positive charge, which means it's lead 4 oxide.